Hi, what's on the workbench today is a UNI-T UDP3305S programmable linear power supply. UNI-T is sending this unit for me to review. As usual, I will leave a product link in the video description below, so you can find out more about this power supply at your own leisure. In an electronics lab, there are a few things that you can never have too many of, in my opinion. One is multimeter and the other one is a bench power supply. A good quality linear power supply is an absolutely must for anyone who is serious about electronics, whether you are a professional or a hobbyist. And without even powering it on, you can see already that this is definitely a serious lab-grade power supply. The UDP3305S is currently the highest spec power supply offered in the UDP3000S series. Now, the model number might be a little bit confusing, as besides the UDP3305S, there is also the UDP3305S-E. At a suggested retail price of roughly $520, the S version costs about $150 more than the -E version. So what's the difference? Well, if you take a look at the basic specs here, you will notice that both of these versions offer pretty much identical voltage and current ranges. They both have 4 independent output channels. Channel 1 and Channel 2 are adjustable and can output up to 33 volts and 5.2 amps. These two channels can operate independently, or you can put them in parallel or in series. The beauty of this power supply is that the internal relays handle the parallel and series configurations, and there's no need to hook up any wiring externally. We will demonstrate this in just a little bit. So here are the two channels that I just mentioned. Besides these two channels, we also have this channel 3 that is also adjustable. It can go up to 6.2 volts and has a maximum output current limit at 3.2 amps. And finally, you also get a USB charging port, which can output 2 amps. And that is counted as the 4th channel on this power supply. Now, personally, I would consider the UDP3305S 3 channels instead of 4. As the 4th channel is really just a USB output and it's not adjustable. A lot of power supplies nowadays have dedicated USB power port. Some even have USB-C power port that supports power delivery. Regardless, whether you call this a 3-channel or 4-channel power supply, arguably the inclusion of a USB port is quite useful. So far from what we can see, everything looks pretty much identical between the 3305S and the 3305S-E. But if you look at the programming resolution and the readback resolution specifications, you will see that the resolution of the 3305S is much higher, although the current programming resolution is the same. So presumably, the 3305S has higher resolution ADC and DAC built in compared to the -E version. Now, if you don't need the actual programming and readback accuracy, you can probably save some money and go with the -E version. But for precision lab use, the high readback resolution is definitely a welcome feature. Obviously, being a linear power supply with a maximum output power of 348 watts, this power supply is actually quite heavy. It weighs slightly more than 10 kilograms or roughly 22 pounds. Now let me actually turn it around and show you the back here. So just give me 1 second. By the way, I had to prop it up because the angle is not quite right for the camera. So let me just turn it around here. On the back panel, we have plenty of connection options. You can see we have a USB port, that is a host port, a LAN port, and a USB Type-B port. Some digital I/Os can be programmed either as input or output ports, and you even got a standard RS-232 port. The AC selectors here are mechanical switches, and that is because we have a transformer inside. Through the fan opening back here, you can kind of see a toroidal transformer towards the front half of the unit. Most quality linear power supplies chose to use toroidal transformers because they are quiet and more efficient. Alright, let me turn it back around again and power it on so we can take a closer look at the user interface. The power supply does have a physical button and is towards the front here. Let's power it on. And it boots up immediately. You can see that we have these 3 channels. By default, all the channels are off, as you can see. That is a standard behavior, but I think you can actually adjust it in the settings to make it remembering the last power on state. But this is what I prefer. The basic operation is very intuitive. You can, for example, turn each channel on and off via these buttons here. And also you can turn all of them on and off at the same time. To adjust the set voltage and current, you can use the channel button here to select which channel you are trying to set the parameters with, and then we can set accordingly. For example, we can set the voltage, you press voltage, and we can use the rotary encoder arrows to set different digits, or we can punch in a number using the keypad here. So that is very intuitive here indeed. You can see here 24 volts, and that is set. Now this is the default display setup. By default, you can see all three channels at once, all the settings, the current, whatnot. But if you prefer, you can actually zoom into the specific channels. For example, right now, if I zoom in, you can actually see channel 1 right here. And of course, you go to channel 2, channel 3 settings, you can use the channel selection button to do that. So for example, right now we're setting the current. You can set it again using either the rotary encoder or simply just punch in the number here. By the way, I'm not sure if you can hear the fan in the background, but the fan is actually very quiet. I'm sure once we start to join some load, the fan will probably spin up faster, but right now it is very quiet. Now, one feature I really appreciate is if you look at channel 3 here, we have some of these preset voltages. These are some of the most commonly used voltages, and you can just select instead of having to punch in. So let's give it a quick try here. We go to channel 3. You can see right now we're setting at 1.8 volts. And if you just keep pressing the channel 3 button, you will see that we can cycle through these different preset voltages. Of course, you can always set your own voltage by entering the voltage here. So for example, we want to do 2 volts, and you simply just do 2 volts, enter. Of course, once you set a different value than the preset values, the indicator light is off. Of course, we can always set it back to one of these presets. Now I want you to check out the voltage setting accuracy here. For that, I'm using the UNI-T UT8805E, which is a 5.5 digit bench multimeter. And I just hooked it up with the channel 1 output here. And by the way, the fan noise you hear is actually from the UT8805E, not from the power supply itself. And when I reviewed this bench meter, I did mention that the fan was a little bit on the louder side. As a side note, you can see that the UNI-T products have these rubber bumpers, and then they do stack up pretty nicely. So let's set the output to 1 volt here. And you can see we're reading pretty much exactly 1 volt, 2, 3, 4. That's quite impressive actually. Let's go to 10. Let's go to 15, 20. And you can see that we are essentially only out by a few digits at the very end. 25. Which is pretty much spot on. Let's do 30. Again, the accuracy is very high here. So let's do the maximum here. I think it's 33. Yep, no problem at all. Because channel 1 and channel 2, the specs are the same, I'm not going to test channel 2 independently, but we can actually put channel 1 and channel 2 in series here. So let's do that. You notice that when we change it to series mode, the output actually are all turned off. That's actually a good feature because you don't want to accidentally turn it on and somehow you set it to the wrong voltage and cause damages to the connected circuitry. But anyway, in series mode, we need to use this output and channel 2 output. So let's enable the output. And you can see both channel 1 and channel 2 are on right now. And you can see we're very close to the 64 volts. In fact, we're just a few counts out. And the 2 meters readback, you can see one is from the built-in measurement from the UNI-T power supply, and the other is from the 5.5 digit bench multimeter. They essentially match. So now let's change the voltage downwards a little bit, and we can see, get a sense of the accuracy here. 60 volts, no problem. Let's go 50 volts, no problem. 40, no problem. And you get the idea here. And because the UDP3305S has a voltage set resolution of 1 millivolt, let's actually verify that. So let me go down a little bit so we have 1 extra digit on the multimeter here. So let's do, let's say 5 volts. And I wanted to set the last digit. So you can see here, we are at 5.000. And watch what happens when I increment the last significant digit here. So you can see we changed to 4.9995 instead of 4.9985. So that setting accuracy is excellent. This is quite impressive, you can see here. Anyway, so now we have verified indeed you can set the voltage to an accuracy within 1 millivolt. Now let's take a look at the current setting accuracy here. So for that, I'm going to measure 1 milliamp at a time because that's the minimum resolution we get in current setting. So let's set to 1 milliamp. And you can see we're pretty much exactly 1 milliamp, which is quite impressive, by the way. 2 milliamps, 3, no problem, 4, so let's do 10. And as you can see, at 10 milliamps, the current setting accuracy is even higher. So let's actually keep increasing. Let's do 20. No problem. Let's do 50. 100. That's not a problem at all. Let's do 200. I think that's the highest I can go with the milliamp measurement here. And I just swapped the leads, so we're measuring in amp range now. You can see 1 amp, that's the set current. We're measuring 0.99, which is pretty accurate here. And let's do 2 amps, 3 amps, no problem at all. 4 amps, 5 amps, no issues. And because we can actually parallel channel 1 and channel 2, so let me actually do that so we can keep increasing the output current. So to do that, I'm pressing this parallel button, and again, the output is off. So let's actually confirm if these two are the correct output here. Yep, these are for parallel. So let me enable the output. And of course, right now we are at 10 amps. So let's dial back the setting here. You can see that the 10 amp measurement is essentially spot on here. So let's do 9 amp, 8, 7, 6, going back to 5. As you can see, the accuracy of this bench power supply is nothing short of extraordinary. And before I move on, let me just quickly show you a few other features here. If you press the wave button, it will show you each channel's output in terms of voltage and current in this graphic representation. And that is actually very useful if you are, for example, especially if you're programming the output voltage to follow a certain pattern and you want to see the voltage and current measurement. That gives you an indication of the measurement without having to look at the details here. So anyway, so that's that. If you go down, you will see we have a button called list or delayer, and this is actually the button gives you some programmability. So let's take a look. So if you press list, you will see that essentially you can set the voltage according to a specific pattern and have it play back on this UNI-T3305S. And to demonstrate that, let's actually select one from the templates here. So let's press template. And the first one, obviously, you can see we have different waveforms you can output. And let's just see sinusoidal here. So for that, I'm going to go to points. So let's go all the way up to the maximum here. So I think it's 2048. And you can see that the interval is 1 second. So let's actually make it faster. Let's go down. Let's go down to interval. And this one, let's change it to 0.1 second so that we can update this value every 0.1 second. We should be able to see on the multimeter and also on the power supply itself. So okay, so I think what we have done here is essentially varying between 0 volt and 3 volts at a interval of 0.1 second in 2048 steps. So let's start this. I think I have to press parameter again. So right now it's stopped. I should be able to say start up. And right now it's paused. I think it's because the output is off. Let's turn on the output. Yeah, you can see that right now we are actually going through the list here. So let me change the display here to see if we can see any output here. And I just enabled the graph. You can see here we're actually ramping down the voltage very slowly. Now, I think this is probably too slow. So in order to see it more clearly, let me actually reduce the number of points and we'll do it again. And now you can see that's the sinusoidal we're approximating from the signal output. And look at that, that's essentially the sinusoidal here. And by the way, I did have to change the n number to 255 so we don't have that many points, so that we can actually capture a nice sinusoidal on the UT8805E. And let's take a look at the delayer here. So if I press it again, you can see that we go to this delayer menu. And this essentially allows you to turn the output on and off based on a pre-programmed schedule here. So you can see we currently are on at 1 second and the other second is off. So let's actually take a look at this operation here. So I think we start up. Yep, you can see that the output is on and off based on the pre-programmed schedule here. Anyway, you saw that the voltage is actually at 96 millivolts. Let's actually set it to 10 volts here. So we can go back to the delayer and do it again. So let's do 10 volts. And let's go back to the list, delayer, and let's try it again. And we automatically stopped. You can see, I think the reason is because the stop condition is greater than 0 volts. So let's actually change the condition here. And we can come down here and see if we can modify that. So stop condition, let's just do greater than 10 volts. Actually, let's do greater than 20 volts. So we probably won't stop here. So that's actually a condition you can use to control the on and off of the sequence here. So let's actually not worry about the condition here so that we can just demonstrate the on and off of the system here. Right now the stop condition is none. Let's do start up again. And you can see that now we're oscillating between 0 volts and 10 volts with an interval of 1 second. So quite neat, huh? So this is definitely going to be very useful when you are doing some automated testing. Now what I'm going to do next is to generate some load using this electronic load here. And to measure the voltage, to get an understanding of the load regulation, I'm also putting the bench meter directly at the bottom of these connectors here so that we can get a more accurate reading. So right now I'm going to set the current draw at 1 amp. Let's enable the load. And you can see we're drawing 1 amp. And we are not really seeing any voltage drop. You can see here it's 9988. If I turn off the load, it's 9993. So we only dropped a little bit. Okay, so let me increase the current draw here. So let's do that. Set the current. Let's see here. Let's do 2 amps. 3. And you can see we do get a little bit of voltage drop, and that's typical, but this is nothing significant here. And now right now we're drawing 3 amps, and let's do 4 amps. And 5 amps. So you can see the load regulation is pretty impressive. And let me temporarily turn off the load here. Let's see here. So we can now increase the voltage to the maximum so we can dissipate a little bit more power and see whether or not the fan kicks in. So right now we are setting voltage. Let's just do all the way up to 33 volts. And let's do 5 amps. All right, let's enable. So notice we did get a little bit of voltage drop, but that is well within the range. And right now we're dissipating 165 watts, as you can see here. So I guess to kick things up a notch, let's actually parallel these two channels together. I almost forgot there was something propping it up, so that block was shifted here. So let me put that down here so we don't tip things over. Okay, now let's enable the output. And again, let's set a voltage to the maximum here. So let's do this. 33 volts. And let's set the current to 10.4 amps. right now we're drawing 5 amps. And let's keep increasing the current setting here. 6, 7, 8, 9, and 10. So right now we're drawing 10 amps now. And you can see the dissipated power is 330 watts. So let's actually increase the current a little bit more. So let's go here to 10.1, 10.2, 10.3. I don't want it to enter over a current. So by the way, that is the sound from the electronic load, not from the power supply. Well, I have let it run for about 5 minutes now. And unfortunately, you can't hear anything from the power supply because the electronic load is just super loud here. But the fan speed had increased a little bit. Let me just show you here. So let me get my microphone. You can kind of hear this is the power supply. And this obviously is the multimeter. Of course, the loudest thing is the electronic load here. Maybe what I will do is I'm going to turn off the electronic load and also turn off the meter here. So hopefully you can hear the fan noise from the 3305S. So let's do that. And you can just hear how quiet the fan is compared to everything else. And here's the fan noise again. Because it is a linear power supply, the ripple noise is very low. Now, it is specified it should be less than 2 millivolts peak to peak, and we do want to take a look at that. Of course, it's going to be very difficult to measure the actual ripple noise, but we'll try. So for that, I'm having a resistor here. This is a 5 watt 10 ohm resistor. Right now, we're outputting 3 volts, so it's drawing about 300 milliamps. I also hooked up a probe, and right now the probe is set to ×1, as you can see here. So we can see ×1 so that we can eliminate some of the high frequency noise. And of course, right now you can see it's not very clean. That's because the environment, if I just short these two, you'll see that we're essentially seeing nothing on the oscilloscope here. Anyway, so let me try to probe from close to the base here. And this is going to be tricky, but I'll try. And right now I had made contact to both the positive and negative terminals, and you can see we're picking up some ripple noise here. So let's do the measurement here. And roughly here. So you can see right now this is 1.6 millivolts. And of course, I need to, as I said, it's difficult to keep in contact here. So now you can see roughly we're definitely within that 2 millivolts peak to peak specified number here. So the ripple noise of this power supply is very low. Now let's take a quick look at the current ripple noise. Here I'm using the CP503 current probe, and we set the measurement in AC mode so we can take a look at the noise here. And you can see right now, I don't know how well it shows up on the screen here, but we're measuring roughly peak to peak at 6.4 milliamps. According to the spec, the RMS value of the current noise is roughly at 2 milliamps. So this is largely in line with what is spec'd. And by the way, for this measurement, we're still using that 10 ohm resistor as a load. Now let's briefly take a look at the power on behavior of this power supply. Currently, the voltage is again set to 3 volts, and we're not limiting the current. For the load, I'm using this same 5 watts 10 ohm resistor. The oscilloscope right now is set to single shot mode. Let's give it a go. And you can see that the rise time here is measured at 6.62 milliseconds, which is very good. The power on curve is very smooth. There's no overshot. What I'm going to do next is to try to force a overcurrent situation to see how fast the power supply readjusts the output. So let's do that. So let me turn off the output. Let me change the voltage to, let's say, 10 volts. And let me change the current limit to, let's just say, 0.5 amps. So basically, if we power it on, this is a 10 ohm resistor, so therefore it will be overcurrent. I wanted to see how the power supply adjusts. Actually, let me change the current to 0.3 amps because right now we already have this scale set up here. So let me change the current, let's say, to 0.3 amps. All right, let me clear the output and let's start again. And you can see that essentially we don't have any overshot. This is actually quite impressive. And just to verify we're actually limiting the current, let's do it again. So let's, instead of 0.3 amps, let's change to 0.4 amps. And now we should see the curve plateaus at 0.4 here. So let's redo the single shot here and turn it on. And you can see we're showing 4 volts now, and there's no overshot whatsoever. And I just want to test the extreme situation when we set the voltage all the way to the max. Let's do that. So set the voltage to 32 volts. Again, we're limiting the current at 0.4 amps. Now let's give it a go. So let's start this single shot again. And you can see that there is no overshot at all. And one last thing I want to mention is this utility button here. If you press this, you will get into this menu and you can actually set up the monitor. For example, you can set up conditions, and once the conditions met, the power supply would automatically shut off the output. And this is useful if you, for example, are powering an external circuitry and that circuit usually uses 3 watts. All of a sudden you start using more than 5 watts, obviously you can shut it off. So this is exactly for that purpose. So this scenario can be controlled via this monitor capability. And let's go back to utility here. And the recorder is free to record data points onto the onboard memory. And we have the setup here. Let's take a quick look here. And of course, if you don't like the beeper sound, you can turn it off. The brightness, I wish I had seen this before because this is a little bit on the dim side. Of course, we can change that. Let's go down to brighter. And you can see that it's only slightly brighter, but that's probably where I will leave it at. Let's take a look at the bout. And here is the serial number and also the current software version. Obviously, there's still a lot of features I haven't touched upon. For example, the programmability of this power supply. You can control it via skippy command remotely, and that is essential for automated testing. The digital I/O interface at the back also provides additional freedom when interacting with external controls, which can be useful in both instrumentation and testing. Overall, it's a very solid power supply, and I do like what I see. Again, please check out UNI-T's website if you are interested in this model. Anyway, I hope you find this video useful. If you liked the video, please remember to give it a big thumbs up, and remember to subscribe to the channel for more videos like this in the future. If you'd like to see more UNI-T products featured on this channel, please also put that in the comment below, and I will see if I can make that happen. Again, your participation is crucial for me to continue making videos like this. Thanks for watching, and I will see you next time.